Good morning, everyone. Welcome back. It's great to see you. Good morning. I hope you've had a nice week. For once, I had a week without any planned travel to go give a seminar somewhere. So I decided to, the past few days, drive down to South Bend, Indiana. I mentioned before, next year I'm going to be a postdoc in Notre Dame there. So I was driving around to see where I might want to live. And of course, I was also visiting the university, and they asked me to give a talk about my work on Thursday. So I just can't stop talking about physics, but I wouldn't want to. So I'm glad to be back here to tell you more about cosmology. So you will recall from last week, we switched gears from particle physics to cosmology, and I probably spent a bit more time than I should have talking about gravity. We learned about general relativity telling us that space-time is dynamical, that matter, things like heavy objects like the sun, curve space-time, and then correspondingly, the curvature of space-time curves the trajectories of particles like photons, and I showed you some nice pictures of gravitational lensing as a result. And we started talking about the very early universe when, shortly after the Big Bang, the universe is some hot nuclear soup, some plasma, lots of very dense particles. This is where we're going to pick up from today. And the big questions that we want to ask is, how did we go from this homogeneous, uniform, hot, dense plasma to what we see today, that things on Earth are very unlike the average place in the universe, unlike some random spot out in space, and also, how do we go from just having protons and neutrons to the elements in our body, things like carbon, all of the nuclei that we need to live. So that's where we're going over the next couple lectures. Let me get into it. So I want to say something that I sort of implicitly said last time. I wanted to say it more. We have, in the early universe, a hot, dense soup of particles. And whenever we have lots of hot photons, and their energies, or their temperatures, are much greater than the mass of some particle, for example, a quark, then from the special relativity, which we've talked about from mass-energy equivalence, you have production from the photons of, say, quarks and antiquarks, in general, particles and antiparticles. So just saying that we have a very hot, dense environment implies that not only do we have things like photons, but lots of our particles, all the particles and antiparticles in equilibrium. And it so happens, we've been able to understand from cosmology, there were lots of particles and antiparticles, but there were ever so slightly more particles, some 1 part in 10 billion. So for every 10 billion antiprotons there was 10 billion and 1 protons. There was some slight matter asymmetry. Now the physicists, cosmologists understand theoretically how this might have happened, a process known as baryogenesis. And if there's interest, maybe I'll go into that in a couple lectures. We haven't been able to observationally test the mechanism of baryogenesis, why there was this slight asymmetry, although we have some good ideas. So in keeping with the sort of philosophy I've suggested, that we're going to talk mainly about what we've really observed, understood both theoretically and empirically. We're just going to take this as an initial condition that indeed we know from the cosmology that I'm going to get to today that there was some slight imbalance in the very early universe. And this means that when the temperature drops, so at very high temperatures, you have both of these processes going on very frequently. Photons, because they have energies where they can create the mass energy of a quark or a proton, whatever it is, they transfer to particle-antiparticle pairs, and likewise, the antiparticle-particle pairs frequently get together and annihilate back into photons. You have both directions going frequently, but when the temperature drops down below the mass of this particle, then your photons no longer have enough energy to create a particle-antiparticle pair, but the particle and antiparticle are still attracted to each other, say, electromagnetically, and so they can still annihilate back into photons, and so you have only this one direction, say, a proton and an antiproton going back into photons after the universe cools below the mass of the proton. And so all of these symmetric components, these 10 billion protons and antiproton, very quickly after the temperature drops below their mass, annihilate back into photons. You're left just with that one very small amount of the asymmetric, very, very small additional amount of protons over antiprotons. Okay, so this was some important background that was implicit in some of the things I said. Well, I tried to say a little bit last time, but I thought I should get back to. So we have, you saw this slide already last week, we have a few seconds after the Big Bang, the temperature in units of Celsius is something like 100 billion degrees, incredibly hot. We have protons and neutrons. As I was just saying, this is at temperatures below the mass of the proton, so the protons and antiprotons have all annihilated away. There's just this small excess amount of protons left. We're still far above the mass of the electrons, so you have lots of electrons and positrons around. They're all interacting very frequently. Additionally, neutrinos. And so I talked last week about, well, we're very far from something like atoms being able to form. The temperature is something like 100 billion degrees. The binding energy, keeping the proton and the electron together in a hydrogen atom, say, corresponds to something like 150,000 degrees. So if you tried to very briefly form a hydrogen atom, it would essentially immediately be ripped apart by all of these very hot other particles. And this is the situation. And not only that, although we have now, it's cool enough that we have protons and neutrons, you recall, those are also bound states. At these sorts of temperatures, they can't pair up yet into nuclei. But you saw this briefly last week. As the temperature of the universe cools below something like 10 billion degrees Celsius, I'll remind you, space is expanding now, following the Big Bang. So space is expanding and things are getting more dilute and correspondingly cooler. So eventually, something like a timescale of 5 or so minutes, the temperature drops low enough that neutrons and protons can get together to form deuterium. And we talked last time about how this is, in some sense, the most crucial step. There's sort of a barrier to forming deuterium, but once you form deuterium, then additional neutrons and protons can be captured in a nuclear fusion process to eventually form helium, which is helium-4, which is sort of where the matter wants to end up. And we talked also a bit, we saw in the first part of this series more on particle physics, we saw that the neutron is unstable. There was a great question about the relative stability of the proton and the neutron. While the proton, as far as we've been able to tell, is stable, the neutron is unstable, can decay into a proton and an electron and a neutrino through the weak interaction that we talked about. And it turns out that the lifetime of the neutron is something around 15 minutes, comparable to the age of the universe when these Big Bang nuclear fusion processes are occurring. So there's some competition between neutrons wanting to find protons to bind together with to form these nice stable helium nuclei and the decay of the neutron. And I should repeat the mindset here. What we're doing is we're taking all of the particle physics that we understood in the first lectures and nuclear physics, although I didn't spend as much time on nuclear physics, but the particle physics and the nuclear physics that we can understand from making measurements today, and porting that into the early universe and trying to understand the physics of what happens with the particle species, all of these particles that we know from today in this setting of the very hot early universe. And we can understand this quite precisely and quantitatively.
Question?
Brief question, sure.
How do they explain how the electric charge got on the electron?
On the electron. No, so as we've talked about a bit, charge is a property of particles, just like energy is a property of particles. So the electron always had its charge. You can't talk about an electron without its charge.
Is it an energy?
Is it an energy?
Is the charge energy or a substance?
Neither. It's a property of particles. There can be energy associated with charges stored in, say, electromagnetic fields, just like there's energy associated with mass. But charge is a property of particles. It tells how different particles interact with, say, the photon, or with other of these gauge bosons, these vector bosons that we talked about earlier in the course. But we can talk more later. Let me go on. So this is a plot from a review article about a decade ago on our understanding of Big Bang nuclear synthesis. I just want to show you some, real research level understanding. Sometimes to get across that really there is some quantitative, detailed understanding behind all this. You can look at the top axis here. It's telling you the time in seconds. It's logarithmic after the Big Bang. And you start off with just neutrons and protons. They're labeled hydrogen because they just care about the nucleus. Hydrogen nucleus is just a proton. And the neutrons, contrary to the protons, the neutrons are decaying over time. So you have some small negative slope in the abundance of the neutrons, but eventually the universe gets cool enough, and if you like, the temperature, well, I haven't explained these units, but the temperature is going down this way as time goes forward. Eventually, the temperature gets cold enough that hydrogen, protons, and neutrons can stably bind together to form first deuterium, like we talked about, this red line, and then helium. Some poor notation, but Yp here is the mass fraction in helium-4. So we understand quantitatively what should happen. You start the universe off with the familiar particles we know about from particle physics and nuclear physics, and you can play forward what the abundances of everything should be. And we can understand from nuclear physics how these larger nuclei are formed in Big Bang nuclear synthesis. And it's not just, I should also emphasize, not just a model, but it also matches our observations, right? So when we are putting particle physics and nuclear physics in the setting of the hot, dense early universe, there is really only one free parameter past the particle physics we know about today to determine what happens in the early universe. It's essentially what I said already. It's how much of an imbalance there is between particles and antiparticles. This very small, well, around 1 part in 10 to the 10 billion or so. And so, that makes this theory of Big Bang nucleosynthesis a very powerful theory. You just have one free parameter to try to fit, to observe. And what you can do is take those calculations that I was showing on the previous slide as a function of the value of this parameter, which is what's changing on this axis. These blue lines are the predictions for the abundances of the various elements as a function of this one free parameter. And then astronomers can go out and look at some very distant old clouds of gas whose abundances still reflect the abundance in the very early universe and measure these things. And they can find, for helium, say, it's roughly a quarter of the mass in baryons goes into helium. That's these green bands are the observations from the astronomers. Helium-4, this is helium-3, another isotope of helium with only one neutron instead of two. You have this green band of measurement there. This one's deuterium, and they all match our blue, the green observations all match our blue predictions at this one particular value of the asymmetry of matter and antimatter, which allows us to measure it. And it really is a marvel of precision cosmology that we can understand this precisely. And furthermore, okay, I'm doing things, saying things a bit out of order. This gray band is an entirely independent measurement from what I'll get to presently, the cosmic microwave background and the Planck telescope. That's also sensitive to this matter-antimatter asymmetry, and the entirely independent measurement we do in the cosmic microwave background exactly matches what we see also from Big Bang nucleosynthesis. So we have some nice consistency between cosmological measurements that, as we'll get to in a second, take place at very different times. Now, let me mention parenthetically, because it's good that I occasionally emphasize that science is not complete, physics, cosmology are not complete. There has been, for decades now, a confusion over lithium. Lithium, this is the element with 3 protons. Deuterium and hydrogen have 1 proton, helium 2, and we match those. We match data and theory fantastically there. For lithium with 3 protons, there's actually been a persistent mystery. You can see here the region where the blue theoretical prediction for lithium and the green observational detection, well, measurement, do not lie in the same place as the rest of them. This has been a persistent mystery in cosmology. I should say, measuring lithium is far harder. There is much less, I didn't emphasize the axes here, but you go from helium-4, which has about a quarter of the abundance, is abundant in about a quarter of the baryonic mass, down helium-3 and deuterium are about 1 part in 100,000, that is. Lithium is far rarer at something like 1 part in 10 billion again. So it's much harder to measure. We can't measure it in exactly the same way. So there's some reason to be skeptical that this measurement isn't really accurately getting the primordial abundance of lithium. I mention this partly because if you take this seriously, you should think about alternate models of particle physics and cosmology that can account for it, and some of my recent work has been on proposing a solution in physics beyond the standard model to address the lithium abundance and to make our theoretical predictions actually in accord with the observations seen. But time will tell whether there really is a problem in our understanding of Big Bang nucleosynthesis for lithium, or whether it's the measurements that we need to understand better. And once we properly measure lithium, it will again match what we thought from the rest of Big Bang nucleosynthesis. Good. Now, so that's Big Bang nucleosynthesis. We've done some nuclear fusion to create some helium nuclei. And so after something like, well, 15, 20 minutes, the universe finally falls below 1 billion degrees Celsius, still incredibly hot, but now you can have nuclei that have stably formed and won't be destroyed by background, say, photons. And we have now protons and helium nuclei. The positrons and electrons at this point have all annihilated. The temperature is below the mass of the photon, so we don't have any positrons around anymore. We just have these electrons. And also there are still neutrinos around, although the neutrinos have stopped interacting with everything else. The temperature is low enough now that the weak interaction is no longer efficient, and neutrinos only interact with the weak interaction, not with photons. So they are decoupled from the rest of the species. They're off doing their own thing. Everything else is still talking through photons. And I should remind you, just again, things are still incredibly dense. It's not just one of each thing. Many particles, and this is not at all to scale, really. You should remember, for every one of these blue blobs, every one of these protons, there are something like 10 billion photons. So I couldn't quite draw 10 billion photons on this slide, but that's what you should have in mind. The universe is still very hot and dense, and as a result, we don't yet have atoms. We still can't form hydrogen atoms stably. You'll recall I've drawn this plot now many times. Hydrogen is a bound state of a proton and an electron. They're held together by this Coulomb potential, which properly understood in quantum electromagnetism allows you to derive that there are these bound states that we've talked about. But these bound states, the binding energy corresponds, as I said before, to a temperature of something like 100,000 or so degrees. So when the temperature is very hot, again, photons or whatever other particles hit some hydrogen would immediately break it apart. So you don't have it stable. So I want to emphasize now the change in timescales. Big Bang nucleosynthesis was at something like 5 or so minutes, but again, where the universe continues to expand and to rarefy and cool, the temperature eventually, you wait something like 380,000 years now later, and the temperature finally falls below about 4,000 degrees Celsius, where we're finally down to maybe some sort of temperatures that are, well, close to human accessible. Yes. Good. The temperature falls low enough that now photons are cool enough that if you form hydrogen, you don't immediately get blown apart, but electrons now combine with protons and with the helium nuclei to form now hydrogen and helium atoms. And this is very important. It means that photons, after this, can free stream. What should I draw? Let me see. So before this, the universe is a charged plasma. We have lots of separate positively charged nuclei and negatively charged electrons around. And because the photon interacts with everything that is electrically charged, at these high temperatures where you have all these charged particles, photons very frequently interact with all of the particles in your plasma. The sort of, what do I want to say? The interaction length, the free streaming length, is very small. If a particle emits a photon, it very soon hits something else, right? But once we have protons and electrons bind together, yeah, good. I should change color, maybe 2 colors. Good. So when you have, and this is very schematic, of course, but now that protons and electrons are bound together into something neutral, right? The atoms are neutral, the positive and electric charges have been balanced out, so the universe no longer has this sea of charged particles, and now, after you have atoms form, the universe is mostly neutral, and so photons can now, well, we say free stream. They can travel without hitting anything else. Okay, I didn't actually say explain the title of this slide. This era, epoch of the early universe, is known as cosmic recombination. The name is purely for historical reasons because this was first discussed before we actually understood Big Bang cosmology. But in fact, the protons and the electrons are combining for the first time now. And because after the charged particles combine, you're left with a neutral universe, photons can free stream, and these can come all the way from 380,000 years after the Big Bang, free stream through the entire history, now some 13.8 billion years of the universe to us on Earth. And I think I said at the first lecture, but I'll say again, that if you recall your analog television and mistuning it so it wasn't quite on the right station, some part of that static you saw was really the afterglow of the Big Bang. It was your television picking up on these cosmic photons that had been traveling for nearly 14 billion years. Wow. So this phenomenon wasn't first measured until 1965 by this team of Penzias and Wilson, who won the Nobel Prize for it. They had a microwave telescope, and they discovered that if they pointed it at different places on the sky, no matter where they pointed it, there was some cosmic microwave background of photons coming at them. So this was sort of a lucky sort of discovery. They didn't go out to look for it, but they were trying to do astronomy and look at the universe in the microwave. But they found that wherever they pointed, and this is a simulated. They didn't actually do a full sky survey. This is a simulated image from NASA of what they would have seen. This central bit is the plane of the galaxy, which has many microwave sources of its own, which is really what they wanted to look at. But they found that all over there was this background of photons at a temperature today, which is, well, 2.7 Kelvin, or in degrees units, something like minus 270 degrees Celsius, coming at them from all directions. And it's hard to overstate the historical importance of this. This was really the first good, very convincing observational evidence for a hot Big Bang. This put to bed what people were asking about a couple weeks ago, the steady state universe idea. This really showed that, in fact, sometime in the early universe, we had the universe had been very hot, and we could observe the afterglow of the photons from when matter and photons, or I should say charged fermions and photons, decouple. So this was really a revolution for our understanding of the universe. It wasn't for a few decades that and I don't know the history whether this was more politics or we needed to better build better telescopes. But in the early 90s, good. So Penzias and Wilson in the 60s had just seen the same temperature of photons, the same energy of photons coming from every direction. In the early 90s, we sent up another microwave telescope that could measure much more precisely the energies of these photons. And astronomers observed that even though indeed the zeroth order conclusion was that the temperature of the universe was homogeneous, there were in fact these incredibly small inhomogeneities. When you looked with incredibly good precision, you could find that at the level of 1 part in 100,000, there were some spots that were ever so slightly hotter and some spots that were ever so slightly colder. Again, this red region now, again, is noise from our own galaxy emitting microwaves. But if you compare a relative hot spot like this yellow blob here to a colder region, a blue blob here, the comparison is something like one is at, say, 2.70000 Kelvin, and this one is 2.70001 Kelvin. So very small inhomogeneities. Yes?
Quick question. Did they in fact show that the distribution is oval like you're showing here or not circular?
Sorry. This is a particular, thank you. The question is about the shape of this plot. This is a particular projection of the celestial sphere, say. Just like when you look at Google Maps, right, they're doing some Mercator projection to go from the sphere down to a flat, presented to you sort of on a flat plane. Here, we're trying to picture the universe, the entire sphere in one flat image, and the way that the cosmologists like to do that, I don't remember the name of this projection, but is to map it to this oval sort of shape. Thank you. I should have said that myself. Good. Yeah. So you can think of this. Well, this is a line toward the plane of the galaxy and not the plane of the solar system. But you can think that this is sort of the south pole of the galaxy, the north pole of the Milky Way. But they're trying to get the entire observable sky onto this one image.
Doctor, it looks just like your tie.
Yes. Thank you. It is a similar
tie.
It is a similar color scheme to my tie. That was not on purpose, but a happy accident.
You're going to throw me out.
Good. So we've seen the observation of just the homogeneous, the zeroth order conclusion that the universe, there's this very roughly the same, almost exactly the same temperature from each direction. That was great toward confirming that there was something like a hot Big Bang, the paradigm of Big Bang cosmology. But now we see it's not actually uniform. There are all of these inhomogeneities. And that's great, right? Because one of the things we want to understand is how we get to today a very inhomogeneous universe. So it's great to see we have this fantastic data. We get a snapshot of the sky at around 380,000 years ago. Because these photons, years after the Big Bang, 13.8 billion years ago, because these photons have been traveling since then, and we can now try to understand what physics was behind these inhomogeneities, what physics had happened in the time preceding the cosmic microwave background, this era of cosmic recombination, what had happened that had created these inhomogeneities. And so, the physics is that of gravity, right? The point, as we've talked about before, is that everything feels gravity, unlike the case of electromagnetism, where we have positive and negative charges. Everything, all energy, gravitates, and in an attractive sense. And so, if you started off with any sort of tiny deviation from homogeneity, if there was slightly more energy in this part of the universe than that part of the universe, well, there's also more stronger gravity in this slightly stronger gravity in this part of the universe. But over time, that means that this slightly more dense region of the universe gravitationally has greater gravitational attraction and attracts more matter into it than a slightly less dense region, right? And so gravity causes these inhomogeneities, some initial incredibly tiny inhomogeneities, to grow over time. But you'll remember from, well, you might remember from, say, just high school chemistry, that gases, interacting gases, like the standard model plasma of photons and electrons and protons, have pressure, right? You can think about just a box and some gas with gas being lots of particles which are traveling some random directions, and depending on the temperature of the gas inside, they have some pressure against the walls of the box that makes it hard to, say, squeeze them into a smaller volume. This is sort of the explanation of pressure that you'll get in a chemistry class, and roughly the same thing works here. It is the case that because our standard model particles are charged, they're interacting with photons, that means they have this pressure, they have some resistance to being forced into a smaller volume. And so this pressure serves to counteract the effect of gravity. Gravity wants to attract things in to an overdensity, but things don't just immediately fall in, they have this pressure. This is a figure from a well-loved cosmology book by Scott Dodelson, who was a professor at the Kavli Institute here, but I found also a more modern animation, so thanks to the creator of this, and just to illustrate that you have some overdensity, some region of the universe which is slightly more dense, and indeed there is a gravitational force attracting things to that region, but because of electromagnetism, because our particles are interacting with each other, there is a pressure that fights also against this. Now, our particles have this pressure. I'll mention it will be a quantitative question. Now we're going to try to understand the physics of our standard model particles in the early universe, like I've been saying, and we can try to track how these inhomogeneities would grow in the early universe, given both gravity and the fact that our standard model particles have pressure. And it will be a quantitative question as to whether that will match the spectrum of the amount of inhomogeneities that we see in the cosmic microwave background. Now, I'll say, because, well, you probably know what the answer will be anyway, if we had some other sort of matter which did not interact with our photons the way that all of our standard model particles do, well, roughly, then you could have some matter which did not have this same sort of pressure against falling into gravitational overdensities. So this is the phenomenon of dark matter. Since it does not feel that pressure of the photons trying to prevent it from falling into potential wells, it could cause gravitational inhomogeneities to grow more rapidly than our standard model particles can. Okay, and I might have one more animation. Yeah, good. This is an animation by these guys who were instrumental in understanding how to compute the CMB. What they do, which should replay, hopefully, what they do is they will start off, maybe I have to click it to make it replay, it will start off, there we go, with an overdensity, start off with a small overdensity in all of these different sorts of particles. Dark matter, gas here means the protons and electrons, photons, neutrinos. They'll start off with some small overdensity, and what they're showing is how the different sorts of particles respond to a gravitational overdensity, a region of larger density and gravity. Dark matter, and okay, I should also say this animation really goes far, far beyond what we're talking about today into next week's topic of eventually galaxy formation. The M years here is millions of years, whereas we're only going to, today we're only going to a few 100,000 years. But what you have is the dark matter only interacts via gravity, and so can stay, and as I've been saying, fall into a gravitational overdensity and deepen it. There's some sort of runaway process. More gravity means more things are attracted to it, means more gravity, etc. Whereas in the standard model plasma with photons and protons and electrons, because there's this phenomenon of pressure, a small overdensity sets up, in fact, sound waves. Right? We've talked earlier on about that, that sound is nothing but pressure waves in a fluid. And so in that exact sort of way, you have sound waves in the standard model plasma, and this is the sort of physics you need to understand to properly account for how the inhomogeneities grow, for what sizes they get to. And so, this is a beautiful image. This is the most recent iteration of an all-sky map of the cosmic microwave background from the Planck telescope. This datum release might have been in 2013. And now you can see we have astonishingly good resolution. I mean, I can't even capture this on this projector. Now we have astonishingly good high definition mapping of the cosmic microwave background, and can see in incredible detail which parts of the universe which parts of the sky are very, very slightly cooler or hotter. Again, this is the scale here between a reddish blob and a bluish blob is 1 part in 100,000 difference. So we have from the Planck telescope this fantastic map of the cosmic microwave background. And to understand things quantitatively, we want to, well, with our physics theories, we predict sort of the sizes of these blobs that are these regions that are slightly hotter or colder, and you can turn this image into a more quantifiable thing that you can compare your physics theories to. So this is good. So all of this, all of these cosmological measurements, that this study is done in the language of statistics, and what I'm plotting, well, what the Planck team is plotting here is a statistical measure of just how big those blobs are. I mean, you could probably see sort of by eye, you could see by eye that there is some sort of characteristic size. I mean, you have lots of different sizes of hot and cold regions, but there's some sort of characteristic size, and in fact, you can quantify this. This is what's known as a power spectrum. That isn't important, but this quantifies roughly how many hot and cold regions you have on different sort of angular scales and sizes. And so there is one characteristic size about 1 degree. These red points here are the data from that picture I just showed. This is the power spectrum of that picture. Very large features really aren't present, but there is some characteristic size, and then the physics of, well, these sound waves of the inhomogeneities growing allows you to precisely understand this oscillatory feature, all these features in the data, the sizes of these various peaks. This green band here is the theoretical prediction. So, cosmology, the cosmic microwave background is now a precision science. We understand from our theory with, again, quite few free parameters, again relating to now how much dark matter, things like that. With very few parameters, you get this absolutely beautiful fit to, an incredibly non-trivial fit to the data, to understand very precisely how big the inhomogeneities are at that point in time. As we continue moving forward through the universe down to today, and in particular, you find that the standard model matter that we talked about throughout the first part of the course is actually outweighed by how much dark matter there is, by something like a factor of 5 to 1. Not just do we need some additional component, some additional particles that don't talk to the photon, but in fact, there's even more of it than there is of our sort of matter. Okay? And dark energy we'll get to next week, I promise. Great. So, I should emphasize, and dark matter will come up more next week as well, I should emphasize, we've seen the gravitational effects of dark matter in the cosmic microwave background, and next week in the shape, the distribution of galaxies in the later universe as well. We have not been able to detect a particular dark matter particle yet. This is an incredibly active area of research, both in theory and in experiment, looking for dark matter. And its particular interactions. People build enormous detectors to try to wait for a single dark matter particle to come in and interact with our standard model things to try to understand in more detail the nature of dark matter. But we haven't yet detected precisely what dark matter is. But following, we had some discussion, I asked last week if it was okay for me to go slightly outside my plan of only talking about I thought there would be interest also in some discussion of how we think dark matter might have been produced. And in fact, although in some sense dark matter is mysterious, we don't know exactly what it is, you find when you go and write down models of particle physics beyond just the standard model, which we talked about, we already need physics beyond the standard model for lots of particle physics reasons, neutrino masses, the hierarchy, the Higgs hierarchy problem I talked about. You find that when you go writing down models of particle physics to address these, it's very easy to also find that some dark matter is produced. So it's nothing, from a modern perspective of understanding the standard model of particle physics, it's not terribly surprising that there is additional matter that doesn't interact electromagnetically. Let me explain what was for a long time the leading sort of paradigm for how dark matter might be produced. This is, so this is the paradigm of weakly interacting massive particles. I write just in case you've seen or you see the acronym WIMPs. That's what's being discussed. Good. And the idea is to consider a particle, I guess I've named on that slide X, to consider a particle which doesn't interact with electromagnetism, right? It doesn't have an interaction with electromagnetism, or the photon, because it doesn't have an electric charge. Again, we're thinking about what properties this particle is going to have. If this particle X has an electric charge, it will interact electromagnetically with the photon. But if it only interacts with the weak bosons, we saw earlier on that the Standard Model also has these vector bosons, the W and the Z bosons, which unlike the photon and unlike the gluon, these are very massive. This is part of what the Higgs mechanism does for us. You might remember the Higgs doing spontaneous symmetry breaking gives a mass to these guys. So now again, when we're in the very early universe and the temperature, the energy of everything, the temperature is much higher than, say, both the mass of this X particle and also our Standard Model boson masses, then you can essentially ignore the masses. Everything's moving incredibly quickly, they have very high kinetic energies compared to their rest energies, and things work just like here, where you have, again, you have this interaction because X has some weak charge, but not a photon charge, but it works just like this case, where at very high temperatures, these hot photons can convert back and forth with a pair of charged particles and antiparticles, electrically charged particles and antiparticles. Again, in the very hot early universe, you have that same process here, where Z bosons have so much kinetic energy that they can create an X and anti-X pair, and likewise, X and X bar can annihilate into these heavy bosons. But eventually, just like happened here, eventually the temperature will fall below these masses. That's CW. Okay, and then eventually the temperature falls below, and like before, the photon. Sorry, what do I want to say? When the temperature falls below the mass of this new particle, then the vector bosons have a difficult time. They don't have enough energy to create it. Just like here, when the temperature fell below the mass of, say, the proton or some quark, the photons no longer have enough energy to create proton and antiproton pairs, say, but proton and antiproton pairs can still annihilate back into photons, right? So this is how the overall symmetric component, which you had tons of antiprotons and protons, this is how those annihilate against each other back to photons, and we're left with just the small asymmetric component in the Standard Model. In the case of this weakly interacting dark matter, you have a similar thing start to happen. When the temperature falls below that mass, your bosons can no longer freely produce these particle-antiparticle pairs, but then, since these bosons have a mass themselves, unlike the case of the photon, eventually it will be the case that the particle-antiparticle pairs no longer have enough energy to go this way either. You won't end up annihilating all of the dark matter particles with their antiparticles back to Standard Model Z and W bosons. You will have this process for a while, but it will be cut off at some temperature. And that's what happens here. This black line is what happens in the case of an electrically charged particle. You start with a whole bunch of, this is an abundance, you start with a whole lot of that particle, an antiparticle, and then the temperature is cooling this way, temperature cools, and when you get toward the mass of this particle, it starts annihilating against its particle, and eventually, if it has an electric charge, so it annihilates to photons, massless particles, it just annihilates completely away, or any symmetric component that is. But if you don't talk to photons, but only some massive W or Z bosons, then eventually this is cut off. This is just some different parameter choices. Eventually, these antiparticle-particle annihilations are cut off, and you're left over with some additional weakly interacting massive particle that has not annihilated away, but no longer interacts frequently with anything else, because the weak interaction has these massive bosons. At cold temperatures, particles stop interacting through it. So you freeze out, you have some leftover abundance of these dark matter particles. So it's really a very simple way to create dark matter, and this paradigm of weakly interacting massive particles dominated the field for decades because it was so simple. Now, we haven't seen anything, and it's still possible that dark matter is a WIMP, but people have, in recent years, been interested in investigating alternate paradigms, and indeed have found that there are lots of other ways to produce dark matter. This plot is taken from a paper where they suggested, in contrast to a freeze-out mechanism, something they called freeze-in, where you started with zero dark matter and eventually built it up over time from some standard model production. But in general, the sort of thing I want to get across is that we have lots of ideas, a huge variety of ideas for what dark matter might be. This is showing that people have talked about different sorts of dark matter over a humongous range of masses. And also with different sorts of, they can't interact with the standard model particles, but in principle they could interact with themselves. So people have thought about tons and tons of different ideas for what dark matter might be. This is an incredibly active topic in particle physics theory and experiment. We're looking for lots of these sorts of particles, and certainly some of my colleagues might have done a Compton lecture series just on all of the different sorts of ideas of dark matter. As you know, I wanted to do something broader, but I wanted to show this is a very active area of research now. And even though, in some sense, dark matter is mysterious, we don't know exactly what it is yet. We have lots of good ideas. It's not like something where we're totally in the dark. We don't have any good explanations. We're just sort of waiting to figure out observationally which one of these possibilities is actually borne out in nature. Okay, a lot today, but we saw the formation from the very, very early universe of nuclei, of atoms. I hope the short bit about dark matter was interesting as well. Next week, we will continue further on to talk more about the growth of inhomogeneities, which eventually produces structures like galaxies and eventually like stars, which are key toward producing the atoms that are actually in our bodies. And I look forward to seeing you then. Thank you.